good afternoon, everyone. I'm leading a team at Oak Ridge that looks at next generation architectures and tries to pathfind those emerging technologies for a variety of sponsors. And what I'm going to talk about today is some recent efforts we have in DARPA. Before I dive into that, however, I'd like to talk a little bit about the recent trends in computing. And I do this because there's a lot of doubt in at least the DOE community about where computer architectures are headed. And so I'm going to spend a couple minutes talking about that with the goal of convincing you there's almost a state of crisis in software systems and applications at this point. And that is because everyone is having to write specialized code for individual architectures, right? Even in DOE and many other places. That's a big challenge that we need to address right now. Our project is the ORNL Cosmic Project. It's sponsored by the DSSoC program. And we're looking at several of these challenges. The first one is really, how do we even model these codes to know what architecture is appropriate? The second one is, how do we write code that's performance portable, right? So that we can legitimately run it on a couple different architectures at least and see reasonable performance. Third is this idea of intelligent scheduling. Now, on an SMP, a multi-core SMP, scheduling is relatively simple, right? Our argument is that you need an intelligent scheduler because that intelligent scheduler is going to have to know that the GPU can provide 10x performance on specific kernels rather than just scheduling it there blindly. And so what we're doing is looking at some intelligent scheduling systems to try to help with that. And then finally, this is, you can think of this as future-proofing, but we want to target a wide variety of existing and future architectures, both within DSSoC as well as outside that. Some people are looking at agile chip development. If you look at the Turing Award lectures earlier this year, they're talking about agile chip development. They're talking about new chips coming out, on a quarterly or monthly basis. People build themselves. How in the world do you write software for that? It's a big challenge. So, motivating trends, and some of this I'm sure many of you know, but we know that a lot of our contemporary devices are approaching fundamental limits, and there are a lot of papers out there that talk about the end of Gennard scaling and Moore's law. And so that's, physically we know that's also happening. But I think the more important thing is what it's doing to the business of foundries and fabs and other things. If you look at this investments that the different companies are having to make, Samsung, for example, is claiming they have to invest $115 billion over the next 10 years. Just to think about that number, that's about as big as 2/3 of the GDP for 2/3 of the countries in the world, right? That's a huge, huge number that they have to invest in the hope they get it right and that people buy those products. And you also see the number of fabs dropping precipitously there as well. So this is having impact on at least our environment. We're seeing a lot of acquisitions and other business activity where companies are being bought, changing roadmaps, merging, and I would argue at least part of that is due to this complexity and cost that has to be invested, and the inherent risk in that, where they may get it wrong. They may, end up like Intel did, where 10 nanometer didn't work out as well one time as they thought it would, and so you have AMD starting to take big chunks of market share from Intel. So, I'm not here just to be pessimistic, but I like to think of this as basically a sixth wave of computing. If you go back to Ray Kurzweil's book and you look at kind of computing over the last century, I really like this graph because it shows the major epochs in computing. And the integrated circuit one at the end is where we have been. We really benefited from that. You just download, buy the new processor, maybe even not even recompile, and you see some performance improvement. And that's changing. And so, big picture, this is something we're going to have to deal with for the next 10 years, at least, probably. and we've already started dealing with it. Now, I'll give you some examples of that in a second. It's a great time to be a computer scientist, so if you need problems to work on and need opportunities there, it's a good area to be. So what's going to happen during this? So these are my 3 predictions, just to kind of give an overview. The first one's really optimize the software and expose new parallelism. So in DOE, for example, this is something we've been doing with MPI, OpenMP, and other standards for a long time. And so we think a lot of other people are going to have to start doing that too, looking more carefully at their code, understanding where the parallelism is, and then be able to map that to the architecture. Okay. The other thing is kind of the next big thing, the new shiny object, is the emerging technologies, right? So everyone's heard about quantum computing, and there's a lot of funding, a lot of initiatives for that right now. The recent report from the National Academy of Engineering suggests that it'll be at least a decade before RSA factoring could be threatened by quantum computing. So there's a lot of engineering and a lot of challenges there. Neuromorphic computing is in the same boat. There's a lot of research going on now. We have advanced digital, where carbon nanotubes have made some inroads. Just last week, one of the other DARPA projects in the ERI program announced they created a 16-bit processor running on carbon nanotubes, right? And so it's very low frequency, but it's interesting progress, right? And then finally, the emerging memory devices. And what I mean by that is all of you have things like flash drives in your backpacks right now. All of those things are really making progress at a rapid rate. So finally, here in the middle is this idea of architectural specialization. And this is really the idea of using the CMOS we have today, but really specializing it for workloads. And that means you're not just having a bigger cache or maybe a little faster core or a few more cores, but you actually take specialized functionality and you put it on the chip. It also means integrating the components to boost performance, so you may not have to ship data back and forth between your devices. And it really means paying attention to memory and storage as well. And so that's what we're seeing across the board for the most part. If you look at Google and Amazon and Facebook and Anton, a lot of other processors, that's what's happening right now. At Hot Chips, for example, the big semiconductor conference, there are a lot of announcements about specialized SoCs for machine learning and autonomous driving and many other areas. Plus you have things like GPUs, obviously. And the mobile market has really led this trend. If you look at this, the iPhone 11 was just announced. We don't have a chart for the iPhone 11 yet, but if you just look at Apple's processors, they've been growing dramatically in the number of IP blocks they have because they've identified specific functionality that have a power performance improvement that they decided to put on the chip. And then finally was this idea of the RISC-V ecosystem. And so that's, again, that's growing rapidly. I think they're expecting almost 2,000 scientists and engineers at the RISC-V Summit this fall. And it's open source. You can go download Verilog for various cores and use it in your design. So just to close the circle on this, so this transition period we're talking about is going to be disruptive. There's a lot of opportunities and a lot of pitfalls. If you look at this chart I've adapted from IEEE Rebooting Computing, the point of it is the darker colored cells really mean you have to rethink everything in the stack, right, or in that layer of the stack. The things, the lower layer, like the new carbon nanotube transistor, you may be able to cover up and hide. But something like quantum computing or neuromorphic computing, you may need to redesign your entire algorithm to make use of that. And so we've been seeing this at Oak Ridge. So for the past 8 or 9 years, we've seen a movement toward graphics processors in our large-scale systems. And unfortunately, at Oak Ridge right now, we have the #1 system on the top 500. It has 27,000 voltage GPUs in it. It draws almost 10 megawatts. And it has these tensor cores on it. So if you're thinking about machine learning these days, you can think about a peak of almost 3.3 exons. Now, the question is, does your algorithm make use of those? And I would argue this is an example of a specialized architecture that was created for machine learning, and we need ways to be able to program those and make use of them. The next system that we have is also going to be a GPU-based system, and it is a AMD GPU-based system, and so it's going to be about 1.5 exaflops, and it's going to be focused primarily on the AMD GPUs where you're getting your performance. And so just looking at this, so if you look at all of the architectures we have, there are three main trends. The first one is the heterogeneous cores. It started with Titan, and Titan was just turned off about a month ago, but it had GPUs in it from NVIDIA. Summit's going to have GPUs, or does have GPUs. Frontier will. Aurora is an Argonne system. It'll be an exaflop system as well, and it'll have Intel GPUs, and then El Capitan out in the far right will be provided by Cray. The choice of accelerator hasn't been announced yet. So the other thing is that memory hierarchies are changing rapidly, as well as plateauing I/O performance. And so, just to summarize on that, we're seeing a lot of these effects in DOE, and in the applications teams are primarily climate and other types of large teams, right? Recently, DARPA started the Domain-Specific System-on-a-Chip program to address similar challenges, but for streaming types of applications. And this includes things like vision and software-defined radio. These are the 5 performers right now for this program. It's program manager is Tom Rondo, who you heard from earlier. But we're trying to address some of the challenges of heterogeneous processing with this. I'm going to talk about our project called Cosmic. And so it's a whirlwind tour. There's a lot of things to cover, but I'll try to do the best I can in the next 15 minutes or so. So think big picture. So I come to you and say, I've got 1 billion transistors. What do you want on the chip? How do you decide that? And so the first thing we're trying to do is come up with a methodology to look at SDR applications and then decide what needs to be migrated in the hardware you're putting on the chip. And we're doing that with a technique called ontologies. Ontologies is really a way to break up all the functionality that you have in something like the GNR suite or OOT suite and look at it and understand what functionality is necessary. And then you can map that onto different accelerators, for example. The second thing is the actual chip design, and 3 of the projects in DSSoC is building chips. They're building chips, so we're expecting to see new chips come out of this program. We'll have to write software for, and then those chips will be shipped and used in a variety of test beds and prototypes. The programming system can also take advantage of that ontology because in the end you need to understand what the connectivity is between the different modules as well as the data movement. Runtime scheduling is the same way. If you're doing dense versus sparse, you're something like a random memory access. All of those things can influence the downstream software stack decisions that you're making. And then at the end, we have what we're calling a performance functional API. And what that does is really allow you to feed information back. Now, why is that important? It gets back to this runtime scheduling. So if you look at the runtime scheduler, it really needs to understand how long it's going to take to finish a task that it's currently computing. And that's really hard to do in most cases. You can do things like count flops and count cycles, but we're trying to understand how we could use that introspective layer to feed information back and talk about where to schedule the next task. We've broken this down into several basic categories that I'm going to talk about briefly. Applications, the compiler, DSL layer, the runtime system, and then the performance modeling on the left. The performance modeling is really the glue that pulls this all together. And the reason that's true is because it gives you foresight. It gives you a way to predict what the next computation runtime may be, as well as which device might provide the best performance. So just to give you an idea of the hardware we're looking at right now, we want to look at many, so we're targeting all these devices right now. We have the Summit node that we're looking at with 6 voltas in it, an EGX workstation that has 4 voltas in it, AMD's Radeon ARM Thunder X2 node. We're also running on an FPGA, the Stratix 10. More interestingly, I want to get back to this Xavier, which is a system on a chip. And as you see on the right, this was made primarily for autonomous driving and other types of tasks. But it includes an inference engine, it includes a vision processor, it includes Volta GPUs and ARM cores. And so all of those are in that one SoC. Also, you've got Qualcomm Snapdragon. And so another very, very popular chip. I'm sure there's some of these floating around. It has a similarly complex organization in terms of the functionality and cores that are provided. It has its own AI engine and other types of video and audio processing. And so that's the applications that's the hardware we were looking at. I want to say a little bit about the applications, but since you're the target application area, many of you know a lot more about this than our team does. But what we're looking at doing right now is having something like a Xavier running on each side, running a workflow, and being able to have an end-to-end workflow running on both of these SoCs. And we're using GNR to do that. In this example, we're just using the Wi-Fi protocol to be able to transmit the data back and forth. And again, the goal was not to come up with a new SDR workflow. It's to make sure that we can accelerate those individual modules using some of the technologies that I just described. So since we were new, we went to the GNR meeting last year in Henderson, which was a lot hotter. But we wanted to try and profile and understand kind of everything that went into GNU Radio, just from a clean slate perspective. And so we went in and started doing a lot of application profiling. We built some tools that allow us to profile the different codes. We'll make those available. In fact, I have a link here in a moment that you can look at. This will be really important when we're looking at what accelerators to put on the chip and what pieces of code we need to accelerate. We have several different scripts that can digest everything you have basically in our repo. This includes creating block level ontologies. It grabs a bunch of basic properties out of all of those modules, things like the number of ports and the data types and all of that, so you can organize it and look at it. The second one is really a flow graph characterization. And what it does is it automatically runs all of those and generates profile data that give you some idea of what's computationally intense about that module. And then finally, there's really a design space exploration where you can run 13 blocks and get some idea of what the scalability and functionality is on different types of heterogeneous devices. And there's our URL. And the slides will be available so you don't have to write these down right now. The other thing that we did was look at proximity analysis. And so what this means is we looked across a subset of all the workflows to identify modules that appear near each other in terms of being connected many times. Now, this is, at first glance, just something trivial. But the idea is that if you have functionality you want to put in hardware, you may be able to take some of these connected components and really fuse them together and actually provide one component to do that hardware activity. And it very clearly identifies what some of those components are. That's in the URL that I gave you. moving on, looking at Aspen, this is the performance modeling tool. Now, again, why do we need that? We need to be able to figure out what the components are, how they're connected, and what their performance characteristics are. So Aspen is something we created about 9 years ago. It's a performance modeling notation, and basically you have some source code. You can digest the source code with compiler and create an Aspen code. You can write the Aspen code out, in an editor, an Emacs or something. And then once you have that, you can use it for a lot of different things. And that can be design space exploration or feedback to a runtime system. And we've demonstrated that in multiple occasions. We're trying to adapt it now for SDR. So what does that look like? So this is the GNU Radio flow graph, an Aspen model conversion that we've done so far. What you see on the left-hand side there is really a high-level view of the overall workflow, right? And that pulls together the components and the important parameters, and it allows you to kind of get a feel for what that workflow looks like. Sorry, back up. So the box on the right shows you what the output or the performance model is for this one of those specific modules. And that's important because that really gives you an indication of what the computational complexity is going to be, right? And in many cases, we can generate these models automatically or with just a little bit of assistance from the compiler tools and other things. But this is really informative. If you have one of these files for every one of the modules, it really gives you a way to figure out what the compute ratio, the memory intensity of individual modules are. The last one is complexity. Everybody's typed LSHW at one time or another. Our architectures are getting far more complex than that. And so what we're creating is an abstract machine model that basically lets you write out what the different components are. And the syntax here is, it exists, but it's somewhat arbitrary. We're trying to come up with a way to describe the different functionality in these devices so that it will make it easy to map and schedule code onto these devices. So the compiler and programming system is one of the things that we've been working on for several years. What we do there is we take an approach so that you don't have to write CUDA or OpenCL at that level, so that the compiler can actually generate code for that target, and then you can hand it off to a back-end system or a just-in-time compiler. And so the compiler we have is called OpenACC. The important thing to realize is with OpenACC, it really takes OpenACC directives or OpenMP4 offload directives and can generate a high-level intermediate representation. Now, for those of you familiar with LLVM-IR is a very low level. This IR is much higher, and what it captures are things like nested loops, it captures kernel launches, it captures data transfers. And so with that, we can pass that off to things like our auto-tuner in order to find out what the perfect mapping is for a specific architecture. And then we generate that from the back end, and then the runtime basically takes it and runs it on the architecture. What are some of the targets we currently support? Right now, we support all these, and most of them are through OpenCL. There's a lot of people kind of questioning OpenCL. We find it portable. It's almost everywhere. There's a lot of potential in OpenCL just for that purpose, and so we've been focusing on that. More recently, we've been looking at generating code automatically that's targeted toward a specific architecture, like OpenMP, for example, or for generating the FPGA-specific OpenCL you need to run on Altera for Intel's FPGA. And so this is just an example of the performance analysis that I was mentioning earlier. We took a few of the blocks and run them and found out what the actual performance was for different buffer sizes of these individual GNR blocks. And this is generated by our compiler. this also tells you a little bit about the actual performance predictive capabilities of the compiler itself. So moving on to runtime system, I just wanted to hit some highlights here. The runtime system, as I mentioned earlier, is really important. And I think over the past decade or more, we've kind of simplified a lot of the runtime systems and really made them really fast, but also really simple. And so what we're thinking is having a runtime scheduler that looks like this. And this is something that we're actually building on now. But it's really a framework for programming extremely heterogeneous systems. So you can take a bunch of tasks that are perhaps from many different applications, feed them to this intelligent scheduler. The intelligent scheduler has multiple queues. It can take those and map them onto the PEUs of the different devices that it has available. It has things like dependencies, so it can manage those dependencies as well as the data movement between the devices if there needs to be data movement. Again, the actual tasks themselves would be generated by the compiler. They look right now kind of like OpenCL tasks, or slightly higher level than OpenCL, but they get fed to this, and they're basically on that granularity. And this is an example of SDR. So we've got multiple workflows here. If you just pick one, which is the one in the back, you can think of getting some parallelism out of the pipelining, and then you can get some task parallelism out of the different modules you have in the graph, and then each one of those may have some data parallelism. You stack on top of that multiple workflows running on the same device, and that's where the scheduling can really benefit you, because it can map those individual tasks on the individual hardware components. The current system we have looks like this. I know it's got a lot of details in it, but our compiler can generate, again, a variety of code, OpenCL, HIP, CUDA, and it can then lower it and hand it off to the runtime system. Once the compiler generates that code, along with the dependency descriptions and so on, it can get queued up into the runtime system. And then the runtime system looks at the different devices and the type of code that needs to execute, and then farms it out to the appropriate device. And right now, we support all of these except the Qualcomm GPU. We have OpenCL working on that, but right now we still don't have it completed yet. We recognize dependencies, so across those devices you can have dependencies, and the system itself, the runtime system itself, can orchestrate the data movement looking at those dependencies, so it knows where it should be when it starts executing. This is a kind of a different view. This is what you see when you're actually starting to execute. You have a ready queue and a task scheduler. That task scheduler, you can make choices many different ways. And this is what I was getting to earlier, where you have a very simple scheduling policy, such as round robin, or just the first thing on the queue. There are a lot of things you can do there. There's profiling, there are user-driven hints, there are the ontology scheduling, there are performance models like Aspen. And we're not quite ready yet to be able to evaluate all those, but that's really the next step in what we're doing. And so we want to be able to have all those events from the SDR application queued up, and then be able to map it to a specific accelerator based on, initially, just hints from the user about that task running well on the GPU. As I mentioned earlier, this task scheduler also has to know kind of how deep the queues are for each one of those, and then be able to recognize that it's going to take a long time to finish the work they're already doing. Finally, the introspective layer that I mentioned earlier is something that we started out really not having an introspective layer in our runtime system. We're adding that. This includes things like just using the performance and power counters, even use things like a temperature sensor to feed that back, and perhaps include that in the runtime system decision making. Now, it's questionable whether you can do that effectively or not, because there's all kinds of challenges like aliasing and being able to close that loop quick enough. that's something that we're hoping to examine in more detail next year. So just to finish up, so, you know, I hope I've convinced you there are a lot of opportunities coming in computer architecture. And, you know, it's going to get worse before it gets better. Take my word for it. There are a lot of challenges coming in these new architectures. The software systems really are not ready, and we need ways to focus on performance portability so we don't have to rewrite every code for every platform. Our ORNL Cosmic project is really looking at the design and programming challenges for SDR, and we're focusing on the things I mentioned earlier: performance modeling, being able to do performance portable compilation, intelligent scheduling, and then, you know, it's not enough to get excellent performance from one architecture. What we have to do is be able to pick this code up and run it across, you know, 5 or 10 architectures and get 80% of the performance you would if you had to do it manually with an expert involved. And so that's what we're focusing on now. So with that, I thank you for your attention and be happy to answer any questions you have.
Thank you very much.